Hello, my name is Rasmus Benestad. I will talk about how global warming affects rainfall and temperature where you live. And this is part 2 of a 2-part lecture series. I will talk about some recommended practices for downscaling. I will also talk about some technical aspects. And the type of downscaling I'm going to talk about can be performed on servers and desktops and laptops. So this is a way of doing climate science on fairly lightweight equipment. In the first lecture, 2 approaches to downscaling were introduced, one involving regional climate models, or RCMS, in dynamic downscaling, and the other empirical-statistical downscaling, or ESD. And these 2 approaches make use of different sources of information. So in the regional climate models, the source of information is embedded in the primitive physical equations and the parameterization schemes, which represent the unresolved small-scale processes which the models do not simulate skillfully otherwise. And the parameterization scheme needs some tuning in order to match what we see in the atmosphere. Also, the results need to be bias adjusted because the regional climate models are not so accurate and they may be off in terms of a few degrees in temperature and also rainfall. So they require empirical data for both evaluation and bias adjustment. When it comes to empirical statistical downscaling, the source of information is embedded in the empirical data and also the statistical theory. So basically, that means the mathematics of the statistical theory. And empirical statistical downscaling require empirical data for both training and the evaluation. And also, the empirical statistical downscaling and the regional climate models have different strengths and weaknesses, which are independent of each other, which is also, one thing that I usually encounter is that when I talk to people who run regional climate models, they're not really interested in ESD, which is a shame because ESD is really useful for regional climate modeling, both in terms of diagnostics to understand how the models work, and also to study how the models simulate cross-scale dependencies. And furthermore, it's actually possible to use both in some so-called hybrid downscaling, or using the results from a regional climate model as a pseudo-reality to train their statistical models. This is also called emulation. So these 2 methods are really useful for each other. Likewise, the regional climate models are useful for testing the statistical methods used in ESD. Before we go on, I want to say something about bias adjustment. What is that? So we know that regional climate models and global climate models often have biases, which means that the temperature may be off by a certain amount, or the variations have different magnitudes to the observations. It is important to realize that the model results are not directly comparable to the observations because they represent different things. So whereas the temperature or the rainfall is a sort of point-size measurement that represents a very small area or a volume, the models calculate the volume averages over several kilometers, so they're not really quite comparable. So the bias adjustment is a way of trying to make the models look like what we actually observe, and the bias adjustment is different to empirical statistical downscaling because the downscaling grabs the large scale that the models are able to simulate and its dependency to the local scale to actually say what the local scale is to infer, whereas the bias correction takes the point size of the model, which is basically on a smaller scale than that the models are able to simulate realistically, and makes a correction to that. Next, I want to talk about some recommended practices when it comes to empirical statistical downscaling. So I will start with downscaling statistical parameters, and then I will talk about ensembles, and then I will present some techniques to maximize the signal-to-noise in the predictants, and also I will talk about some techniques to ensure the quality for the predictors from the global climate models. Then I'll talk about downscaling approach and how to validate. And also I will say something about the validation of ensemble results as opposed to individual models. So this slide shows some probability density functions for Malaga. So this is a temperature, it's called a PDF. And for the temperature, which is close to normally distributed, then we have two parameters, the mean and the standard deviation. But we can also talk about probability distributions in terms of other types of characteristics, for instance, in time, where we have the autocorrelation, or we can have different types of PDFs, like, say, the gamma distribution for the rainfall. The important thing is that these statistical characteristics are influenced by the physical conditions of the system. And the statistical characteristics are often more predictable than the individual outcomes, and often we get more robust results as well. So, whereas opposed to the regional climate models, which predict day by day, and we get the sort of the weather approach, the ESD also allows to predict the shape of these probability distribution function of the climate approach. And just to give you some examples, statistical characteristics are often remarkably predictable, and the local climate can be described as weather statistics. So, for instance, the daily temperature can be represented by a probability distribution function. And here are two examples. And one example here is the daily temperature, which can be represented as a normal distribution, which has two parameters. It has a mean and a standard deviation. And basically what we want to predict or project how the statistics changes. So basically how this probability distribution changes. And it could change by, say, that the mean increases and also maybe the standard deviation increases too, and that would change the shape of this distribution function, which also describes how the temperature statistics is changing. When it comes to 24-hour rainfall or daily rainfall, we have a different situation, because we have, for temperature, there's always a temperature, but for rainfall, it doesn't rain every day. So basically what we need to do is to divide the days into when it rains and when it doesn't rain. And then we can look at the amounts that we receive on the rainy days, and we find that the exponential distribution gives a fairly good approximation of the rainfall statistics on the wet day. So this slide actually shows how we can work in terms of the temporal domain and statistical characteristics of how the June, July, August temperature behaves. So we're looking at the mean length of the intervals above 20 degrees centigrade. So along the x-axis here we have the mean temperature, and then on the y-axis we have the mean interval of, or the mean length of intervals above 20 degrees. So the warmer the mean temperature, the the longer intervals you tend to get on average of higher than 20 degrees centigrade. And the red symbols here represent data from the European Climate and Assessment Data Set, ECHA. So these are actual temperature records. And the gray lines, the gray dots here are just theoretical values if you had a normal distribution. So these are basically like a Monte Carlo simulations. And you will see that there's, even for a perfect normal distribution, you have a scatter here at the top here because you have few data numbers. So one is actual data and the other one is Monte Carlo. And then we have like this Poisson fit here. So we can actually estimate what we expect the the mean length of intervals would be once we know the mean temperature. We can also look at, in addition to spell duration, we can also look at number of events. So we can use the geometric distribution for the duration and the Poisson distribution to estimate the number of events. So the statistics of these events depends on the large scale conditions. So n, which is the number of events, for instance, is a function of the large scale, which is x. And this is actually taken from a study, and we used a generalized linear model to make these curves. And you can look at this QR code here to actually find the reference. This slide here shows how we can estimate the probability for heavy rainfall amounts. So we have two parameters. We have the wet day frequency here and the wet day mean precipitation, which is mu here. And these two parameters can be estimated from the daily data. And then we assume that the distribution of the wet day amounts follows an exponential distribution. So that means that once we estimate these two parameters, we can estimate how often we get more than, say, 20 millimeters, as shown in the example here, or 30 millimeters, and so on. And you can see a test of this from a rain gauge record from Norway. So the black line is year by year. Each year we estimate what the probability of getting rainfall more than 20 millimeters, and then estimate the frequency based on that, because it's the 365 days a year. And the red curve shows the observed frequency, and you can see there's actually a very nice fit between the two. And this study is from a paper, and the QR code you find here. And we try to test this formula for large amounts of daily rainfall records, so from the whole of the world, where we could find free data, available data. So you have both from North America and from Europe, and also some from Russia, and some also elsewhere as well. And you can see that we tested this formula for various thresholds, 10, 20, 30, 40, 50 millimeters. So we had more than 2 million data points, and we get a correlation of 0.98. You can see this is actually a heat map with a logarithmic scale. So the yellow lines here are about 100,000, whereas the red ones are just a few tens. So you can see that this formula is actually very, very useful, because it gives a very good approximation of the observed frequencies of heavy rains. So once we have this formula, then our aim is to then try to downscale these two parameters, what their frequency and what their mean precipitation. And once we know that, we can say something about heavy rainfall as well. I also want to say something about how to use ensembles when it comes to downscaling. So basically, if we have two small ensembles of too few global climate model simulations, then we run into a problem called the law of small numbers, and the results are not very robust, because there is a random component in terms of the internal variability, or regional variability. And so in order to get useful climate information for the future, that can only be synthesized from large multi-model GCM ensembles. So we need to move away from single model results. So here's one example. And the problem with the ensembles is that they are not a statistical sample. So they are the global time models may have something in common. They may have I'll say, all being limited to the same sort of region in phase space, where, like in theory, the true answer could be in the whole of this blue space here. So here's, let's say that the true value is here, and you see that some models may be a little bit off, but like many are overlapping, and it doesn't give like a proper description of the probabilities of this space where the true value may be. So this example B here is more like what we would expect if we had like a proper statistical sample that the models are independent and they sort of overlap the whole space of possible truth results or the truths. So the main reason for using ensembles is because the natural variations are non-deterministic, especially so on local and regional scales. So this example shows like the rainfall in an area mean of 4 models used in a Norwegian some Norwegian reports, and you can see that they have like the decadal variability can fluctuate quite a bit, and these are fairly random. And here you can see the distribution of results for the change between 1900 and 2010. So the ensemble itself actually looks quite Gaussian. So this example here shows how to carry out robust downscaling. And this example is the temperature in Poland. And we have both regional climate models and empirical statistical downscaling. And it's important to include both because they have different strengths and weaknesses, which are independent of each other. So if they give the same results, then we have more confidence in the results. So this example shows global climate model runs, all 108 runs from CMIP 5 RCP 4.5. And we also have dynamical downscaled results, so these are the RCMs, from 9 runs from the Eurocodex runs. So they only represent a small number of the whole ensembles. And the dynamical downscale results are shown in blue here, and you also see that they're only shown for certain times, time slices, because the dynamical downscaling is very computationally heavy, so we can't afford to perform it for all models at all times. And then we have the empirical statistical downscaling for all the results. So here you see the spread of the raw global climate models, and the gray ones are the downscaled results for all of these models. And the blue here are the range of the dynamical downscale results with the subsets of the models. And then also the red spread here is for the empirical statistical downscale results for the same models as the dynamical downscale ones. And this actually corresponds fairly well. And here is also the GCMs for the dynamical downscaling. So you see that this downscaling actually affects the results to some extent here. But the important point here is that when you pick a small number of models, as we have done for the Eurocodex, then we risk getting like the models in the same part of the range of all the models. So this is actually not representative for the whole ensemble. And we show that in the next slide here. So this is again the same case, and you can see that we have the RCMs here in red and blue, and ESD, that's empirical statistical downscaling, are in gray here. And you can see how the raw GCM temperatures compare with the downscale results. And you can see that for the RCMs, they don't capture the whole scatter or the whole ensemble. So ESD can be used to downscale different information to the RCMs here. This slide shows the effect of the ensemble size on the downscaled results. So we started off with the RCP 4.5 ensemble with 108 members, but many of the members were run with the same model. So some models have repeated runs and some had just one individual runs. So the blue results show the results when we just assume that all members are equal and we don't look at what model produced the results. And then the orange results show when we just picked one member for each model. So we just took the first one for each model. So here you see that to the left, here's a full ensemble, and that has 108 members. And there's only one combination of that, and that is just the full sample. And as we use fewer and fewer ensemble members and have more ensembles, then we can get more and more combinations of these the full ensemble. So we have like combinations of sub ensembles which are sampled at random. I just picked like say random 5 members of the 108 members many times, and you see that the mean result is not very strongly affected, but you see that the scatter or the range is quite strongly affected here, and you can see that the range is really affected by the ensemble size. So now we'll want to talk about techniques to maximize signal to noise in the predictants. So what we do is actually we look at many data series in one go, and then we make use of something called principal component analysis to estimate how like the structure of how all these temperatures vary, because they tend to vary in a synchronous manner. So we analyze the set of stations together rather than one by one, and that puts the emphasis on large-scale covariance, and this is also what is more likely to be connected to the large-scale conditions, and that actually improves the signal-to-noise ratio. And we can actually show that with the analysis. And here we see the cross-validation root mean square error. So we have the traditional errors here, and then we have the PCA-based here. And we see that the traditional, like when we downscale one by one models, we get higher root mean square error in the cross-validation than when we get used to PCA-based downscaling with many together. And here we have 2 different domains. So red and blue are 2 different areas. So we tested this for 2 different areas. So you can see that it's not just one for one area. And here we also see that when we do the cross-validation scatter plots between the observed anomalies and downscaled anomalies, we see that the correlation of the PCA base is slightly higher than the correlation of the traditional. So it's just marginally better. We also see that when we use a PCA-based approach, we get a better physical consistency. Strictly, the physical consistency is not preserved neither in the regional climate models nor in the empirical statistical downscaling. And the reason for that is that the regional climate models have different energy and mass fluxes out of the boundaries compared to the global climate models. And when the regional model changes the rainfall patterns, that will have an effect on the vertical energy flow and also the humidity in the air, which is not captured by the embedded global climate model. In empirical statistical downscaling, the principal component analysis-based predictors can conserve the intervariable covariance, or like the spatial covariance structure in the predictants. So they actually can provide some consistency. Next, I want to talk about techniques how to ensure the quality of the predictors from the global climate models. So I mentioned the common EOFs in the first lecture, and these common EOFs are used as framework for the statistical downscaling. So we call them the common empirical orthogonal functions, or common EOFs, for the predictors. So we have reanalysis and we have graded global climate models. For instance, here in this illustration, we can call the dataset 1 is the reanalysis, and dataset 2 is the global climate models. Or we can also have several global climate models here. So what we do next, we take the anomalies of the reanalysis, we take the anomalies of the global climate models, and then we regrid the global climate models onto the same grid as the reanalysis. And then we add these data in the same data matrix. So first we take the reanalysis, and then we append with global climate models in time, and then maybe other climate models. And then we perform an ordinary EOF analysis on that. And the nice thing is then that we get a set of principal components, we get a set of spatial patterns, and we get eigenfunctions as shown below here. And we know that the corresponding parts of the principal components of the reanalysis and the climate models refer to exactly the same spatial patterns. So the spatial patterns are identical between the two. So and the principal components tells how much weighting that should be applied to the two, which means that we can take the part of the principal components which represents the reanalysis, and that can be related to the observations to calibrate the models. And then we can take the corresponding part of the principal components representing the global climate models and use them as input to the same models to make projections for the future. And that way we can use them also to do the downscaling. So the next slide, I want to show a schematic how it's done. So we have the common EOFs with here one set of reanalysis and one global climate model results. So in this schematic, we have combined the spatial dimension on the y-axis here, and the spatial dimension, we combine the longitude and latitude, and maybe even height as well in one dimension. It doesn't really matter because it doesn't have to be ordered in this type of analysis. And then we have a time dimension along the x-axis. So first we have the observations, and then we have the model results. And then we subject this combined matrix to something we call singular value decomposition, or SVD. That's a way of estimating the EOFs. So there are different ways, but singular SVD is a choice here. And that will give us three products. One matrix U, which contains the spatial patterns, and then one matrix sigma, which contains the eigenvalues, and then we have the principal components here, which is V. That's one example. So we have downscaled one result here, and then we get the maps of covariance structure, like where we have the strongest correlation between the predictant and the large scale structure. And then here we have the eigenvalues, so we can see that the leading mode explains most of the variance. So that's like 65%, and then the subsequent modes explains just smaller details. And then the black curve here shows the original data, or the original principal component, because this one in this example we downscale a set of series, so like a principal component analysis results. And then we have the model, which is in red here, we show that they have quite similar variance. So the model actually reproduces quite well the covariance structure seen in the reanalysis that was connected to the local predictant. So to reiterate, with the downscaling of common EOFs, we have calibrated the models, and then we use the part of the predictants representing the model results as input with the same model to make a prediction. So when we compare the common EOFs approach versus a traditional perfect approach where we project the patterns on top of each other, then we see that if we choose predictors with different domain size, like different areas of predictors, you see that the darker symbols here are the common EOFs, and the gray ones are the more traditional perfect prog method. We see that the common EOF approach seems to give more robust results because we get more the same results regardless of the size of the domain. Also, we can use these the principal components to say something about how well the global climate models manages to reproduce at large scales. So we look at the standard deviations of the principal components, of the different parts of the principal components, one representing the reanalysis and one representing models. So we use the ratio -1, so it should be like around 0 for a good match. And this example shows the 20 EOF, so it's actually the blue ones which really matter, whereas the red ones are like just noisy aspects of the models because they don't represent very much of the variance. As you can see, that's here are different models. This is from a CMIP5 ensemble. So you see, some models have are better able to reproduce large-scale patterns than others. Next, I want to talk about the downscaling approach and validation. So one thing we can do when we do the downscaling or before we calibrate the model is actually to detrend the data. So we remove the linear trend in a predictor and a predictand, and then we calibrate the model, and then we add the trend back to the predictor, and then use that as input to the model to see how well it reproduces the long-term changes in the predictand. So here is one example where you have the black curve are the observations, and then the red curves are the predictions after we have calibrated the models with the trend data and then added the trend back to actually see if we can reproduce the results. And this detrending test is a test for stationarity to see if the relationship we use for between the large scales and small scales seems to hold over longer time scales. In addition, we also apply the standard test, which is called cross-validation, where we remove part of the data and do the calibration on the remaining, and then use the part of the predictor that we removed to make a prediction on the independent predictand, and then see how well we reproduce that. So we do that, say, 5 times. So we take 1/5 away, and then we calibrate on the 4/5 of the data and make a prediction for the 1/5 that we removed, and repeat that. So we have covered all the data sets, all the data points, and then we can compare with the original data. So here you can see like across the validation of the temperature in Oslo, we have 0.97, which is very good. And then finally, we also look at this the predictor pattern. So this is a weighted pattern that is of the predictors which correspond to the variations in Oslo. You can see that makes sense, that the temperature in the same region varies with Oslo, and there may be stronger amplitudes here in inland as well. So these are 3 ways of evaluating the downscaling results. Next, I want to talk about the validation of downscale ensemble results, which is different to the downscaled results for a single model. So here's one example. This is the global mean temperature in Oslo. The black symbols here represent the observations, and then the red hatch region represent the downscale results of the CMIP5 ensemble. And here we have also marked the in gray the 5th and 95th percentile. So between these we expect 90% of the results to lie. And if the downscaled ensemble has the same statistical characteristics as the observations, then we expect that 10% of the observations fall outside its range. And we can count the number of observations which are outside. 1, 2, 3, 4, 5 points observations are outside this range. And we expect the number of cases falling outside the 90th percentile range should follow a binomial distribution. So if there are too few outside the region, that means that the ensemble has too large scatter, or if there are too many, that means that the models, the downscaled results do not reproduce the variance well. So, and this diagnostic here shows that basically we have maybe slightly too few outside its range. We should expect to see a slightly more here, which means that the models tend to overestimate the intra-annual variability a little bit, slightly, not too bad. The other way to validate ensemble is actually to look at the historical trend of the same overlapping period. So you can see that the trend of the observations are about 0.07, and then we can estimate the corresponding trends for each of the downscaled results, and then we get like this histogram here. So we get like a distribution, and we see that the observed trend is well within the spread of the downscaled trends.